Okay, now let's look at disjoint events. Events A and B are disjoint, or another phrase you may hear is mutually exclusive. They mean the same thing. If only one of the two events happens. Now, make sure you are aware that this is not the same as independent. It's a completely different concept. This is not the same as independent. In fact, if you know two events are disjoint, then they're not, I can't even spell independent, then they are not independent. Because remember, independent means knowing what happened with the first one doesn't at all give you any information about what's going to happen with the second one. If the events are disjoint or mutually exclusive, then you know if the first one happened, the second one didn't happen. So this is not the same as independent. Example of disjoint events. A football game can't be held at the same time as a soccer game on the same field. Heading east and heading west at the same time is impossible. Tossing a coin and getting heads and getting tails at the same time is impossible. You can't take the bus and the car to work at the same time. Your dog can't be both a purebred dog and a mutt. So if A and B are disjoint, then what we know for sure, so here's another formula for us, is that the probability of A or B would just be the probability of A plus the probability of B. Now, why would that be the case? Well, let's look at this. So first of all, this formula is true only if the events... So it's a very common mistake for people to try to use this formula all the time. You can only use this formula if the events are disjoint or mutually exclusive. That's the only time you can use this formula. Okay, so probability of A or B. So our normal formula for probability of A or B is probability of A plus the probability of B, and then we have to subtract the overlap. Well, if two events are disjoint, that means there's no place where they both happen, so they're completely separate. So if you want the probability of A or B, it's just the probability of A plus the probability of B. There's no overlap that has been double counted. So that's why this will be true if they are mutually exclusive events. So be careful. It is easy to confuse the concepts of disjoint events and independent events, but they are very different. If A and B are disjoint, when A occurs, we know that B can't possibly occur. However, if A and B are independent, when A occurs, it doesn't give us any information about whether or not B occurs, and B could occur. So independent events need common outcomes. Disjoint events can't have any. Okay, so let's do this problem here. About 11% of males are left-handed, while about 9% of females are left-handed. If a female is selected at random, what is the probability that she is not left-handed? So let's do probability they are not female and left-handed. Let's just do FL for that. Well, using our complement rule, this would be the same as 1 minus the probability you are female and left-handed. And the probability you are female and left-handed is 0.09. So this is going to be 0.91. Okay, one male and one female are selected at random. What is the probability that both are left-handed? So you want to know what's the probability you have a male that's left-handed and you have a female that's left-handed. Okay, so when you choose the first person from the population you're choosing from, whether or not that one is male or female or left-handed or right-handed does not at all impact what happens with your next choice. These are independent events because they're randomly selected. So if these are independent events, oh my Lord, why am I having so much trouble with independent? Stop. Okay, if these are independent events, then we know that the probability of A and B is just found by multiplying the two probabilities. So we will have probability you are male and left-handed is 0.11. Probability you are female and left-handed is 0.09. So that is 0.0099. If one male and one female are selected at random, what is the probability that neither is left-handed? So this is very similar to the one we just did, but this time we're saying what's the probability you are not male left-handed and you are not female left-handed. So the probability you are not male left-handed, these are independent events also, right? So because they're independent, I know I can find, just a refresher, all the way back here, if they're independent, then we know the probability of A and B is the probability of A times the probability of B. That's what we're doing here. So we're going to do the same thing. We did that here. We're going to do the same thing here, and I just wrote the notation incorrectly here. If we want the probability that they're not male left-handed and not female left-handed, and I know they're independent events, then that's just the probability they are not male left-handed times the probability they are not female left-handed. Well, the probability they're not male left-handed is going to be 1 minus the probability they are male left-handed. This will be 1 minus the probability they are female left-handed. So that means this will be 1 minus 0.11. And this will be 1 minus 0.09. So that's going to be 0.89 times 0.91, which will be 0.810. Okay, if 3 males are selected at random, what is the probability that none of them are left-handed? So we want the probability that none of the three, oh my goodness, brain broken today. None of the 3 are male left-handed. So that's going to be the same as the probability of not male left-handed and not male left-handed and not male left-handed. Because these are independent events, this will be, we already found the probability, well, let's just write it. This is going to be the probability not male left-handed times probability of not male left-handed times probability of not male left-handed. Again, only because they're independent events. And from the previous problem, we see that the probability that they are not male left-handed would be 0.89. So this will be 0.89 times 0.89 times 0.89. And that will be, not sure why I'm putting parentheses there. That's going to be 0.705. Okay. Let's do one more problem, and this is real similar to problems you're going to do in Wiley Plus and in the textbook and on quizzes and exams. Just a reminder that here are all of our probability rules in one place. If I were you, I would put these on a note card so you have access to them and you can pull it out whenever you need. And you'll need all of these. So I would put them somewhere really handy. Okay, suppose that for events A and B, we know the probability of A is 0.6, the probability of B is 0.3, and the probability of A and B is 0.24. Find the probability of A or B. Well, Formula for the probability of A or B is the probability of A plus the probability of B minus the probability of their overlap. So this will be probability of A plus probability of B minus probability of A and B. So this will be 0.6 plus 0.3 minus 0.24. And that is going to be 0.66. Okay, find the probability of not A. That's going to be the not the probability, how about 1 minus? Not A will be 1 minus the probability of A. So that will be 1 minus 0.6, which will be 0.4. Okay, let's do probability of A if B. So remember our formulas down here. Probability of A if B is going to be probability of A and B divided by probability of B. So this will be probability of A and B divided by the probability of B. Okay, so probability of A and B on this problem is 0.24. Divided by the probability of B is 0.3. So this will be 0.8. Now probability of B if A. So it's the same thing, but notice things are going to be switched. Okay, the given is going to be switched. So this will be the probability of B and A divided by the probability of A. Well, probability of B and A is the same as probability of A and B. And again, think about your picture here. So probability of B and A is going to be this area, and that's the same as the probability of A and B. It's that same area. So I'm going to rewrite this just so it matches our notation above, and then this is still probability of A. So probability of A and B is 0.24, and the probability of A is 0.6. So here I'm getting 0.4. So do you see, first of all, how important it is that you have your correct order for your probability? You have two completely different results depending on which thing is the given. Okay. Now here's another very common question we may ask. We may say, are the events A and B disjoint? Well, look at our formulas here. In order to be disjoint, these two formulas have to be true. So if you can show that they're not, or one of them isn't, then you know they're not disjoint. And so let's look at that first, or that second one. Probability of A and B. What's probability of A and B for this problem? It's 0.24. But if the events are disjoint, what is the probability of A and B supposed to be? It's supposed to be 0, because if they're disjoint, that means they have no overlap. So they are not disjoint because probability of A and B is not equal to 0. Now, we could also show it with the other formula. So the other one that has to be true is probability of A or B has to be probability of A plus the probability of B. Well, we found the probability of A or B on part A. So we know the probability of A or B is 0.66. Is that the same as the probability of A plus the probability of B? No, stop. Is that the same? Well, probability of A is 0.6 plus probability of B is 0.3. That is equal to 0.9. Are these the same? These are not the same. So A and B are not disjoint. You do not have to show both of these. You only have to show one of these. And then last question, are the events A and B independent? So same idea. Here are formulas. If the events are independent, then these two things must be true. And you only need to show one of them. So I'm going to show with the second one here. Probability of A and B should be equal to probability of A times probability of B. Well, we know the probability of A and B is 0.24. Now, what's the probability of A times the probability of B? Well, that is 0.6. A is 0.6 and B is 0.3, which is 0.18. So are these two the same? Right, they're not the same. So A and B are not independent. You could also show it with the other formula, probability of A if B. Well, we found the probability of A if B was 0.8. And the probability of A is 0.6. So I'm looking at this one. If they're independent, then the probability of A if B should just equal the probability of A. But again, these are not the same. So A and B are not independent. And again, you do not have to show that both of these aren't true. This is a sufficient explanation, or this is a sufficient explanation. And that is it for section P1.